So today is our last lecture, one way or another. Homework number, on new material, because homework 12 will be due before I see you next. So Tuesday is safe for review. I'll talk more about the final exam format and stuff like that. First, read the final exam practice logistics. That should give you pretty much what to expect, and then I can make any nudges or answer any clarifications on Tuesday. Also, as of today, I have posted your practice MCAT materials for those of you who that's relevant for. Make sure that you download those because they will not be available indefinitely. So if that's something that might be useful to you in the future, make sure you download them locally. That goes for pretty much everything, all the course materials. If you want to have them later, make sure you get yourself a local copy. But this is especially something that you may not use for some time, so make sure that you store it away. There's some student info and feedback on how the new test differs from the old one, and then the old materials for whatever they're worth, along with various other resources that might come in handy. Okay, so other than that, let's see what we can get done today. I kind of flew through the decibel scale at the end of last lecture, so I want to back up and kind of make sure that we're all on the same page here. So this is the equation for the decibel scale. Basically, you can think of it as the input is the intensity in SI units, and the output is this way of defining volume of a sound in terms of a non-SI way called the decibels. So I gave you some typical intensities in SI units of watts per square meter of typical sounds. 10 to the minus 12 watts per square meter. That's given a special character I naught. It's called the threshold of hearing. It's where our ears start to be able to distinguish a sound from complete silence. The other two examples much larger. Rock concert around 1 and threshold of pain around 10 watts per square meter. And if you run them through this equation, you can get the value in decibels, which greatly condenses the scale down basically from the threshold of hearing to the threshold of pain, 0 to 130. So first, for those of you that may not be that comfortable with working with logs, let me show you that you can do this without a calculator if you ever have the need to do so. First, let me start with I naught itself. So let me put in the threshold of hearing and confirm that you do get 0. Well, in this equation, the intensity of your sound is always taken as a ratio to the threshold of hearing. So in this case, that ratio is 1. If you're trying to take logs of things, the logs of things generally are hard to do by hand, with the exception as if it's 10 to the, because log base 10 is the inverse function of 10 to the. So log of 10 to the x is just x. So this is log base 10, it's not natural log. And so the whole idea here is that that's why we're using a log in the first place. Log is really going to chop things down to size. You have log of, say, 10 to the 14th, some gigantic number. So 10 to the 14th is giant, but log of 10 to the 14th is 14. So we can drastically bring these down to a manageable size. Now, 1 is one of the exceptions where you can express it as 10 to the to make your life easier, because anything to the 0 is 1. So that includes 10. So we can conveniently turn it into something where we can do it by hand. Log of 10 to the 0 is just 0. And multiplied by the 10 in the front, that's still 0. Okay? So we've been able to show with this equation that the threshold of hearing is 0 decibels. That is, in fact, by design. That is why the equation has I naught in the denominator. That is what makes sure that the scale starts where our ear starts. So why not, if we're going to tailor-make something for human experience, why not set the 0 to be where our ear starts? So we're setting 0 decibels to be where our ear starts. You might ask, are there sounds quieter than that? that can be heard by mice and bats and things like that, yes, but on the decibel scale they would be negative. So they are to the other side of 0. We put our 0 where we start. Quirk of some stereos is that they set the 0 decibels not to the quietest sound, but the loudest sound. So does anyone have, it's like a high-end stereo where the reading's always negative and then you turn it all the way up, it's 0? So it's just like setting an origin. Okay, so in this case, most typically the origin is set to the threshold of hearing. I guess we might as well try out another value, which isn't like a trick value. So I might plug in, for instance, let's plug in a rock concert. So that has an intensity of 1 watt per square meter, and I need to take that divided by the threshold of hearing, which is 10 to the minus 12. And then I get log of 10 to the 12. What's log of 10 to the 12? It's just 12. So 12, and then it has a 10 in the front, so that'll be 120. So that's where these values are coming from. Again, if you're comfortable with logs, you could probably just have plugged those in, or just at least comfortable enough with your calculator to figure this out for you. You can do that. So we have that the entirety of human experience is put onto a scale from 0 to 130. The reason there's a 10 multiplier in the front is because a scale of 0 to 13 might be a little bit too compressed. So for instance, you can rank 130 sounds in order of quietness to loudness. That would be a reasonable task. Okay. So one of the things that comes from this 10 being a special number for log, right? You can always take log of 10 to the by hand. You can't take the log of 4 by hand, but you can take log of 10 to the. There's a special property. And so this is something that we always look for shortcuts and relationships and proportionalities and things where we don't have to actually crunch. And for one of the properties of log is that if you multiply your intensity by a factor of 10, that will add 10 decibels. Okay? It doesn't work with any number. It doesn't work with 4. If you multiply your intensity by 4, it's not 4 more decibels. It has to be 10 because 10 is a special number for logs. Okay? So this is an extremely useful thing when you're trying to compare two sound waves, and all you know is that one is so and so many times the other, and you can, you can get it to be 10 or a power of 10, you can easily say how many more decibels is it. Let me give you an example. Let's say I have two sound waves, one of which is 100 times more intense than the other. Well, 100, that's not 10, but it is a power of 10. It's 10 times 10. And so on the decibel side, we have to add 10 plus 10. So it's 20 decibels more. Okay, so if one sound wave has 100 times the intensity of the other, it's 20 more decibels. Okay? So this trick, it works with 10, which is a special number for log, and it also works with powers of 10, because those are just cases where you're multiplying by 10 many times. The general rule is if your intensity is multiplied by a factor of 10 to the n, then your decibels, you have to add that many tens. Okay. Now, for those of you that are comfortable enough with logs, you may note that the property of log is such that the raising something to the power, you can bring it as a multiplier. So if you've worked with log enough, that's where that comes from. The n that is in the exponent becomes the n that is the multiplier. This is an incredibly useful rule of thumb, and coupled with our proportionality relationship between intensity and amplitude, you can go right from comparing the sound amplitude of two sound waves to comparing their intensity to comparing their how different are their decibels. And there are several questions on the homework that ask you to run this set of relationships from either beginning to end or back or the other way. So there are a couple homework problems where I give you that the amplitude of one sound wave is this many times the other. You can say, how does that relate their intensities, and then how does that relate their decibels? I think there's another homework question where I give you that two sound waves are this many decibels apart. How do their amplitudes relate? So you just run it one way or the other way. I can certainly confirm that it works over here. Notice that going from the rock concert to the threshold of pain, that is times 10. And over here, it's plus 10, right? So this seems to certainly be borne out by the values that I ran through the formula the hard way. We can also, of course, go all the way from I naught to the pain, the threshold of hearing to the threshold of pain. If I want to multiply 10 to the minus 12 by a number to get 10, I'm going to have to multiply by 10 to the 13. Okay? So the threshold of pain is 10 to the 13th times more intense than the threshold of hearing. And over here, if I multiply by 10 13 times, that's what 10 to the 13th is, multiplying by 10 13 times. Over here, I have to add 10 13 times, which is 130. So indeed, it's 130 more. Okay, so that's a little bit about the interrelationships, and especially if you're going to take any kind of exam that does not allow calculators, they can't expect you to do logs by hand unless they give you special cases where you can, when there's 10 or powers of 10 relating between intensity and decibels. Okay, and this, by the way, is useful for any kind of log-based kind of thing. The pH scale doesn't have the multiplier of 10 in the front. So for that, if you multiply by 10, you just have to add 1, right? So Richter scale, by the way, is like that as well. So obviously relevant to the Bay Area. Okay. So when you go up 1 on the Richter scale, that's 10 times more energy delivered. Okay. That's why magnitude 8 is such a big deal compared to a magnitude 7. Okay. Every 1 tick up is that much, many times more. Okay. So any quick questions on that? Okay, so I think that's got all our wave basics out there, including for sound waves. Now we're going to start having more than one wave at once. So let's talk about wave superposition. So superposition is a fancy name for a simple idea. Find that. So the idea of wave superposition is that if two waves meet, then what you actually see on the medium is just the sum of what both of those waves would have to say. Okay? So the medium behaves as the sum of all the waves that are on it. So let's take a look at a couple common examples. If you have a crest and a crest meet, let's say both of height A, then they will form a supercrest. Okay? Those could be traveling in the same direction so that they are always together, and so then crest and crest make supercrest that just moves along. Or those two crests could be meeting, passing each other. Then for the moment that they are in the same place, they'll make supercrest, and then when they pass by each other, it's not there anymore. Okay? But the point is, if you ever have two crests at the same point on a medium, they will form to make something bigger. Same goes with a trough. Trough and trough make super trough. Okay? You could also have a crest of height A meeting a trough of depth A, And there, they kill each other, right? So in a certain sense, the crest and the trough will, the crest will be will fill in the trough, and you get back to even, okay? Again, if that crest and trough are traveling at the same rate in the same direction, they will continue to cancel each other out. But if they're traveling in opposite directions, then what will happen is that for the moment they're passing each other, it'll cancel out, but then they'll go right through each other, okay? So we sometimes call this interference when two waves are interacting, and this is specifically constructive interference. For obvious reasons, they're building something bigger than either one is alone. And then this one is called destructive interference, because of course they are basically destroying each other into nothing. So that's the principle by which you would look at any kind of wave interaction, is to basically think of a bunch of independent waves, but if you look at any point on the medium, how that medium behaves, what you actually see with your own eyes, will be the sum of all waves that are present there at the moment, okay? So what we're going to do is we're going to use this principle, and we're going to collide two periodic waves. And we're going to see what comes of it. So first I just want to show you in person what you get, and then we'll pull it up on the computer and we can see a little bit more carefully what becomes of it. So if you wouldn't mind volunteering, you might need to get up. So here I have a medium. It's a kind of a string thing. I can send a wave. Well, let me back up a little further. So I can send a, go ahead and just stay there. I'm just trying to pull it tighter. Okay. So I can send a wave, and notice that it bounces off the end, right? So I have that nice traveling disturbance going back and forth. So since the wave bounces, I don't really need for both of us to make waves that collide. I just need to make a wave and just keep doing it. And when it reflects off that boundary and comes back, if I'm still making the wave in the original direction, then we're going to get our two periodic waves colliding. So let's see what we get. So I'm going to start pretty violently shaking this. You might want to just kind of lock that to your hip. All you have to do is hold it down. Okay? So just don't let it move. So I could get something like this. So it's this kind of nice thing. It looks like a wave that's just kind of floating in place there. It's called the standing wave. A standing wave is what you get when you have two traveling waves that are colliding. And we'll get into how it is possible that a wave traveling right and a wave traveling left ends up being this wave that just kind of looks like it oscillates in place. Let me show you another one. Here's another one. So, oh, you got to hold that in down. Okay? So you notice here that there is a point in the middle that is essentially never moving. Right in the middle, right? So how is that possible that that never moves when I have traveling waves traveling in each direction? Well, what happens is that whenever a crest is coming through of one wave, a trough is coming through the other. So they always kill each other right there. Then you see that there are these other spots which are jumping up and down the most, right? That's where crest and crest are making supercrest at times, and trough are making supertrough. Okay? So what we see is that there are both spots where there is complete destructive interference at all times, right? That point in the middle, that point is called a node. And then there's these other points which are oscillating up and down much, much more than any other point. Those are called antinodes. Now, I should tell you that I, in order to get these, cannot just move my hand however. If I move my hand randomly, I'll get some kind of jumbled mess, okay? So I'll have that how the waves are colliding, it's time evolving, it's not consistent. There's only certain ways that I can actually move my hand to get these special standing waves. So let me try to show you the next one. See, it's a garbled mess because I didn't get the right frequency. Let me see if I can get it. I think that's one too many. I think I have 3 nodes in the middle, right?
Yeah.
So there it is. Okay? So if I can get it just right and I can move my hand just right, I get these standing waves. They don't happen at just any old frequency. They happen at certain frequencies. Okay? So thank you. So let me pull it up on the computer. We can kind of get a sense of what's really happening. Obviously, it's hard to visualize it right there because all we get to see with our own eyes is the medium, which is the sum of both waves. We don't get to see the waves by themselves. We only get to see the two in combination. So let's take a look at what they look like. If this would work. Oh, now there's no internet. All right, well, so much for that. Yeah, that sucks. Yeah, I can't get internet in here, so, well, you're going to have to look at it on your own. I did post this for you. So basically what happens, those points where the nodes happen, the way that that happens is that every time a crest is coming through of one wave, a trough is coming through the other. So they always cancel. And where those parts where the wave jumps up the most, it's where a crest and a crest line up, make a supercrest, and later trough and trough line up, make supertrough. That's what's happening with the antinodes. Okay. So our goal is to figure out what is up with these standing waves. I guess I'm not ready for the next applet yet, so turn this off for the moment. So what I want to do is I want to just draw these guys that I just made. This was the first one. Kind of looked like this. And yes, my hand was at one end that was slightly moving, but I basically looked like this. And then the next one was like this. And then the next one was like this. And they keep going, but this will be enough to find the pattern. So basically the right end is some kind of wall where it's held down, and to all intents and purposes, the left end, where my hand was actually moving, can also be considered where it's not really, I'm not moving my hand that much. So I'll mark these points called nodes, where you always get destructive interference. I'll mark them with an X. And I'll mark these points called antinodes, where you get the constructive interference with an O, because I don't know why. So the first standing wave that I found has an antinode there. That oscillation is the most extreme of the wave. In fact, if you had to guess how much that oscillated, well, if each individual wave had amplitude A, that oscillates back and forth to A to either side, right? That's because that's where crest and crest make supercrest and trough make supertrough, okay? And then I have a node on either end. So this gets a name. So we call this the harmonic, the n equals 1 harmonic. So there's only certain things that work And other things, other frequencies of that I move my hand don't produce these, so there's a discrete set. This is called the n equals 1 harmonic. This is the n equals 2 harmonic, n equals 3 harmonic. And they do continue on. So the next one, this one now has 2 antinodes. So you add an antinode. And you also add a node, because now, rather than just counting the ends of the string as places where the string can't move, we also have one place in the middle where it didn't move. Even though it's in the center of the string, it's because the crest and trough always kill each other. Basically, whatever part of one wave is coming through, the opposite part is coming through the other. Okay? And so on and so forth. As we go down, we are going to add one of each, right? So we're going to have one more of these and one more